I'm interested today in the friction force. Now, I've been talking about friction for 30 years now, but it was a while before I came up with a definition in words for what friction is that was really concise. You can explain just about anything in 1,000 words, but to cook it down to just a few is a bit of a trick. Now, this sentence is really simple, but it contains a lot of information in it. Friction force is the force that opposes the relative motion of surfaces. It's when things slide against one another. Could be a car skidding to a stop. It could be a basketball player moving around on the basketball court. When surfaces are in contact, everybody knows, long before physics class, everybody knows that there is a force between surfaces that we call friction. There's not much difference between what you know from everyday life as the definition of the word friction and our scientific definition. We do have an equation for calculating it, and even right now, there are scientists and engineers who are studying it to understand it better to make new and better materials and products. But for us, the friction force is the force that opposes the relative motion of surfaces. Here's the subtlety. If there are two surfaces, one in contact with the other, and they are not sliding relative to each other, then the friction force acts to prevent them from sliding. But if two surfaces are in contact one with the other and they are sliding, then the friction always acts to stop them from sliding. Well, that was a lot of words. But those words are contained in this. The friction force is the force that opposes relative motion. But there are two kinds of relative motion. Being in contact and not sliding, friction opposes cutting loose and sliding. And then there's the situation of actually sliding. Friction opposes that by trying to stop that motion. Friction force is the force that opposes the relative motion of surfaces. How much friction you get in any given situation depends on two things. The first is the materials in contact. You know from your everyday life that some things are slippery and some things are rough. Two extreme examples of this is if you want to play basketball, you want a lot of friction. So you play in shoes that have rubber soles on a waxed floor so that the friction force is very large because of the materials. When basketball shoes rub against a waxed gymnasium floor, there's a lot of friction force. But if you go on a date with your honey lamb and you decide to go ice skating, you have metal skates on ice because the friction force is very small, which is what you want when you go ice skating because you want to glide along gracefully without the force of friction impeding your motion. How much friction you get depends on the materials that are in contact. And you can see that here in this little cartoon image of, well, I guess a brick on top of a brick. Maybe they're the same material, maybe they're different. But if you zoom in, no matter how smooth the surface is, for example, sitting at your table right now, you might imagine that the surface of your table is extremely smooth. But if we could magnify and magnify and magnify, we would discover that every surface, even the surface of diamond, which has very well organized atoms forming a crystalline surface that is like the ultimate in smoothness, there's always some kind of roughness involved, and some materials are more rough than others. So how much friction you get depends on the materials that are in contact, and also it depends on how hard the materials are pressed together. You already know this. If there's a stain on the table and you use a rag to clean it off, you're using the friction force to remove that stuff from the surface of the table, and you discover that if it won't come off, what do? You start to press harder and harder and harder. The harder two surfaces are pressed together, the larger the friction force between them. If I press my hands together lightly, they move against each other quite easily. If I press my hands together firmly, then I can feel that the frictive interaction between them becomes larger. The friction force depends on the materials and how hard the materials are pressed together. I'd like to do an experiment to measure how much friction I get. The reason why I have to do a friction experiment is because there's no device that I can create that can go in between surfaces and work out how much friction there is. If I want to know the height of an object, I'll use a meter stick. easy to measure. If I want to know the mass, I'll put it on a pan balance, easy to measure. Friction force requires a little bit more cleverness. So here's what I do, and you're going to be doing this in a lab that we have coming up pretty soon. I have this block sitting on the table, and attached to it is a spring scale. And if you pull with some force here, you can measure, it's difficult to see in the image, but there's some gradations on here, some tick marks, and you can measure how many newtons of force you're exerting with the spring scale. But the force that you exert with the spring scale is not the friction force. By grabbing hold of the spring scale and pulling, you're not exerting friction. You're exerting your own pull. The lucky thing is, it is related to the friction. And here's how. I've drawn here a diagram that's intended to represent the block and the forces that act on it. There are two forces on it that I'm not interested in today. Of course, that block has weight. And so I've drawn an arrow downward that is the force of gravity, which is m times g acting on the block. That's awesome. There's gravitational force, but it doesn't come into my interest today. Also, I've drawn this force upward that's labeled N, which is a little bit peculiar. I might have called it F sub N, the N force, but that doesn't clarify anything. It is the force of contact. When the block sits on the table pushes upward on the block. You might call that the support force or a force of contact. The fancy name for it, which we have not emphasized in our course so far, is normal force. The normal force pointing upward is the force of contact. That force is not interesting to me at the moment, and the force of gravity is not interesting to me at the moment. What I'm interested in is that I attach a spring scale to the block and I pull to the right. There you see the force capital F that is meant to represent the force that I pull with and measure. I know how many newtons that force is, but of course, that force is going to be opposed in the opposite direction by the friction force. My diagram helps me get my forces organized. Now I'm going to apply Newton's second law with the force F that I apply to the right and the friction force to the left. Newton's second law, the sum of the forces is equal to the mass times the acceleration. Because the force that I exert is to the right, I've written that as F, minus the friction force, which is to the left, has to be equal to the mass times acceleration. But I am going to choose, in my experiment, I'm going to choose to only investigate situations where the acceleration is zero. There are two ways that that can be true. A thing can be at rest and its acceleration is zero. Or a thing could be moving along with constant velocity and its acceleration is zero. And I promise that in my experiment, I'm only going to consider those two circumstances. If I do that, then the mass times zero is zero. So the force that I exert minus the friction is equal to zero, which means the force that I exert with my spring scale that I measure, the number of newtons, is equal to the friction force. So even though I do not have a frictometer that measures the amount of friction between two surfaces, I can do an experiment where I measure it indirectly. By measuring how hard I pull, I can figure out what the friction is in comparison. So this is the way my experiment goes. I have the block sitting here on the desk, spring scale attached to it, and I pull, and it doesn't move. That matches your experience, doesn't it? Like when you first pull on a thing, it doesn't start to slide straight away necessarily, unless the surface is very slippery. But if the surface is sort of rough, then I start to pull and it doesn't move, and I pull and I pull and I pull, and I'm getting newtons and newtons and newtons and newtons and newtons, but you know what happens. Eventually it breaks loose and it starts to slide. At first it doesn't move, but if I pull hard enough, it breaks loose and it starts to slide. Now, somewhere in your personal experience, from birth to now, you've encountered this sort of thing. The thing is stuck until you push hard enough, and then it breaks loose and can move. This is the nature of the friction force as a graph. Here's what happens. There's a little bit of a narrative. When I attach my spring scale to the block, the friction force is zero. When I attach my spring scale to the block, the friction force is 0. And then I start to pull, but the block doesn't move. The reason why the block doesn't move is I'm pulling to the right and the friction is equal to the left, so that the total force is 0, so that it's force equilibrium. And so I pull and I pull and I pull, and the force gets larger and larger and larger, and larger and larger and larger. And for every newton of force that I exert, the friction responds with an equal number of newtons in the opposite direction. But it can't go on forever. I eventually reach a point where the friction force gives out and the block breaks free and starts to slide. What I would discover on my scale is that as soon as it breaks free, the friction force drops all of the sudden, which is indicated by this kink here on my graph, and the force becomes smaller. Not only that, when I pull the block along at constant velocity, so that the acceleration is equal to 0, it cruises along like this with a constant force. I can tell by looking at this graph that friction has a dual nature. There are two kinds of friction, but I already realized that in my definition of friction. There's the kind of friction that exists when two surfaces are not sliding relative to each other. When surfaces are not sliding relative to each other, of course we have a fancy word for that. The fancy word for that is static. Non-sliding friction is called static friction. But there's a limit to static friction. Eventually it runs out and things break free and slide. The friction associated with sliding is called kinetic friction. The word static generally means not moving, and the word kinetic means moving. So fancy words, but rather easy to tell them apart. Friction has a dual nature. There are two kinds of friction, static and kinetic. To explain why, I want you to consider these rough surfaces here. You can see the texture of the surfaces quite clearly. The reason why static friction exists is when I take one rough surface and put it against another rough surface, they sort of intermingle. You can imagine all of the highs and lows lining up and they're combining together. When that happens, if I push horizontally on it, there's a lot of force. In a way, they're sort of locked together because they fit. If I push hard enough, eventually it will start to slip. And the reason why is the horizontal force that I apply causes them to sort of rise up, and it removes that interlocking, which reduces the amount of force, which I can see on my graph as a sudden reduction of force when cozy locked together, I push hard enough and eventually it breaks free. You can see it bounces along as I go. That's why there's two kinds of friction, because the roughness of the surfaces can interlock, and that creates a non-moving, non-slipping kind of situation. But if I push hard enough, it breaks free of that roughness and then slides one relative to the other.